You guys are pretty smart. I think I can skip the last few rows. You can use those for practice if you like. We are going to do 2 more examples today. One where we see where does that number on the periodic table come from, the weighted average atomic mass that you see on the periodic table. So if I pull up my periodic table really fast, that would be like when we're talking about lithium being the 6.94 or the chlorine being 35.45. Where do those numbers come from? Those numbers are called the weighted average atomic mass, or sometimes I'll use the acronym WAAM for short. In problems where they are calculating weighted averages, they will tell you, they'll give you percentages in the problem. That's showing you what percentage of that particular element is that isotopic form, how common it is in nature. We would multiply that percentage by the mass of the isotope that goes with it, and then add those numbers together. So here's an example. Thallium has 2 stable forms. It gives us the mass of form number 1 and the percent abundance of that particular isotope of thallium. Then it gives us a second mass and percentage of the other isotope. And it wants to know what the weighted average is. So you could see that the thallium-205 is much more common in nature than the thallium-203. These percentages, when you're going to do math, sig figs here in just a second, these percentages called the percent abundance, relative percent abundance, these guys are measured numbers. They measure them using a tool called a mass spectrometer that we're going to learn a little bit more about later in the week. And so they do not have perfect sig figs. What we'll do is do those two different examples there. Okay, so my first line there is I'm going to do the first percentage, switch it into a decimal. So instead of 29.52, I'm going to say 0.2952. And the other percentage, I'm going to make it be 0.7048 instead of 70.48. Then I'm going to multiply those percentages by the mass that goes with it. So the mass of the first isotope is 202.9723 grams per mole. And the other one is 204.9744 grams per mole. When doing weighted averages, you might see either grams per mole or something called AMUs, atomic mass units. The numbers are the same, it's just the units might vary. Doesn't change how you do the math at all. So there's step 1, switch the percentages into decimals. Step 2, multiply the percentage that we just switched into decimals by the mass that goes with it. And then step 3 says to add these two, multiply and add, and get a total. If you were to do that, your calculator would give you an answer of 204.38338. Now, sig fig wise, this does get a little bit messy because we're both multiplying and adding. I would go with the multiplication rule over anything. So you can see those masses have lots of sig figs associated with them, while the percentages only have 4 sig figs. So I'm going to keep 4 sig figs, not 4 decimals, 4 sig figs. So the 2, the 0 is in a sandwich, 4, and this guy, chop. That 8 will nudge that 3 up, so it'll turn into 204.4 grams per mole. If I look up thallium on my periodic table, thallium is right here. Number 81, 204.38, and we had 204.38338. That's where that weighted average number comes from. Something to be careful with when you do weighted averages. There's multiplying, there's adding, there is no dividing. You're used to dividing when we do averages in math class. Add them up and divide by how many there are. When you do that, you're giving equal weight to each number. So if you're adding 3 numbers together and then you divide by 3, you're making it 33%, 33%, 33%. You're making the percentages equal. Whereas when you do a weighted average, you multiply and you add, and it skews the average in favor of the more abundant isotope.